In our today's lecture, we will discuss about designing of sequential logic circuits. We will discuss latches, flip-flops, and register designs by using CMOS technology. I am Dr. Imran Khan. For more videos and technology updates, please subscribe our channel. If you have any question related to our video, please don't hesitate to contact me. Before going to our lecture, we should discuss clocking. As you know, synchronous systems use a clock to keep operation in sequence. Clock helps to distinguish the operation from previous to next operation. Clock also determines the speed at which machine operates. A clock must be distributed to all the sequencing elements like flip-flops and latches. Clock must also be distributed to other elements like memories and domino circuits. So clock is an important part of the sequential circuits design. So we should discuss the naming conventions here. We assume that a latch is a level sensitive device and a register is a edge triggered storage element. An edge triggered register is also called a flip-flop, but the other books can use the different conventions. For example, many other books call edge triggered elements as flip-flops. So we should discuss the difference between latches and flip-flops. Latches and flip-flops are the basic element for storing information. One latch or one flip-flop can store one bit of information. The main difference between latches and flip-flop is that for latches, their outputs are constantly affected by their inputs as long as the enable signal is asserted. In other words, when they are enabled, their contents changes immediately when their inputs change. Flip-flops have their content change only either at the rising or falling edge of the enable signal. This enable signal is usually the controlling clock signal. After the rising or falling edge of the clock, the flip-flop contents remain constant even if the input changes. So here we should discuss the operation of latch and register. So this is a latch and this is a register. So here you can see this is a clock signal, D is input and this Q is output. So here you can see here the clock is at the rising edge of the clock and here the input is high. So the input is high here and here you can see the output is high when we applied the clock. So this output will remain unaffected until our clock is high and input is high. So here you can see. So similarly, in case of register, you can see this is our clock, this is input and this is output. So this register will store information when the clock will rise. So here you can see we have applied the clock. This is the rising edge of the clock and this is input. Input is already high. So here Here exactly below this clock you can see the output will change, so it will remain unaffected until the rising edge of this clock, and here you can see the input is low. There are three important parameters which we should discuss: setup time, hold time, and propagation delay. Setup time is the time for which input must be valid before clock transition. For example, 0 to 1 in case of positively edge triggered register. So here in the next slide you can see this is the setup time. Here you can see, and again we should go back. Hold time. Hold time is the time for which input must remain valid after the clock edge. So here you can see this is the clock and this is the input. So this is hold time. Propagation delay. Propagation delay is the length of time when input is stable and valid and clock transition 0 to 1 in case of positively edge triggered register to the time when output is stable. Usually propagation delay is referred as the maximum time from input crossing 50% to the output crossing 50%. So this is propagation delay. So here you can see this is the 50% clock 50% of this clock input and the 50% of this output. So here you can see this is propagation delay. So we should talk about the overall flip-flop delay. So the total delay in flip-flop is clock Q delay plus delay because of this logic circuitry and the clock and the delay because of this setup time. So this whole will make the total delay of a flip-flop. We can also design our negative or positive latches by using multiplexers. So here we will discuss multiplexer or mux based latches. So here you can see this is a multiplexer. So we can use this multiplexer to design our latch. So for example, this is a negative latch. So negative latch is transparent when clock is 0. So here you can see this is input, this is output. So this negative latch is transparent when the clock is 0 or low. Again, this is positive latch, and the positive latch is transparent when the clock is high or 1. So this is our multiplexer based latch. So this is our multiplexer based latch, and we can also design a multiplexer by using C switches. So here you can see these are two C switches we have placed, and these C switches have replaced this multiplexer. So basically here we designed this multiplexer by using these C switches. So this is called clock D latch with C switches. So we can design our latches and flip-flops by using multiplexers, C switches, master slave, edge triggered register. So here you can see we have used multiplexers to design our master slave register. So this is master stage and this is slave stage. When master is transparent, slave is in hold, and when the master is on hold, the slave is transparent. So we have placed two opposite latches triggered on edges here. This is called master slave latch pair. So here you can see we have applied the clock here. So this is master and this is slave. So we can also use these multiplexers or C switches to design our master slave registers. So we just replaced these multiplexers by using these C switches, or we have just placed the transistors here. This is PMOS and NMOS transistors. So these are the C switches. So these are basically the multiplexers. So this is master and this is slave stage. So here you can see that we can design these master slave flip-flops or registers by using multiplexers or C switches. So this is the block diagram of master slave D flip-flop. So this is master D latch and this is slave D latch. So this is the data input, this is output, and these are two different clocks. One is clock and another is clock bar. So again we have designed master slave D flip-flop with C switches. So in the previous slide, if you see, these are C switches or the multiplexers. So here the block level diagram, and here we just place these C switches here. So this is the input, so this is the clock, again clock bar, so again this is output. So here you can see the output. So when the master is transparent, slave is on hold, and when the master is on hold, slave is transparent. So here you can see the master slave structure. So when you can see the master is on hold, slave is transparent, and when the master is transparent, slave is on hold. So we can design these master slave edge triggered D flip-flops with C switches or multiplexers. So these are two basically clocks. So we have to use non-overlapping two-phase clock, is phi 1 and phi 2, in our latches and flip-flop designs. So this is just an example of non-overlapping two-phase clocks. So we can also design an inverter and C switch by using this tri-state inverter technology. So here this is our inverter and C switch. So we can replace it with our tri-state inverter circuit, or This is a symbol of this tri-state inverter. So this is clock, this is input, output, and here you can see we have applied this non-overlapping two-phase clock. This is output and these are inputs. So we can just replace this circuit by this circuit. So this is the implementation of D latch in clock CMOS. So here you can see we can replace this circuit by this circuit and ultimately by this circuit. So here you can see these two tri-state inverters. So again we have just replaced these C switches by this clock and this clock bar. So again this is the implementation of CMOS master slave D flip-flop. So this is the master stage and this is the slave stage. So here you can see we have applied two clock signals, here and this is called two-phase non-overlapping clock. So this is the master stage and this is the slave stage. So you can see when the master is transparent, slave is on hold, and when the master is on hold, the slave is transparent. So we can design these flip-flop and latch structures by using this techniques. So here this is the implementation of CMOS D flip-flop with enable. So here we just placed an additional multiplexer with enable. So here this is called CMOS D flip-flop with enable. So again this is the master and this is the slave. Again we have applied this two-phase non-overlapping clock and this is the enable circuitry. So we can replace this enable circuitry by using C switches. So this multiplexer can be replaced with C switches. And here we have added this synchronous asynchronous clear. So you can see we can easily design these circuits by using the multiplexers or C switches. So again this is the implementation of CMOS T flip-flop with enable and gated signal. So here you can see we have this is enable and this is the gated clock. So we have placed an AND operation here because when both of our input will be high, this signal will high. So here we have implemented this master slave structure with enable and gated clock. So again we have applied the clock here and here. So this is non-overlapping two-phase clock. So this is same master slave with C switches. We have just added enable and gated clock signals here. So again this is an example of fully dynamic latch based pipelining. So here we have different stages like this phi 1 stage, phi 2 stage, and again this phi 1 stage. So here we have this tri-state inverter. So again, this is some logic circuitry, and we have placed a capacitor here. So again, this is the first stage, this is the second stage. So we have applied the different clocks here. So you can see this is the two-phase non-overlapping clock here in the first stage, and again the non-overlapping two-phase clock in second stage. So we cannot use the same clock in two consecutive stages. So these are different clocks. So again, this is latch based ALU, arithmetic logic unit. So similarly, you can design this arithmetic logic unit, latch based arithmetic logic unit. So again, this is the first stage and this is the second stage. So here we have placed an inverter between the two dynamic states. So this will make the race free condition during the clock sequence. So this is the tri-state inverter here, and here we have placed a static inverter between the two dynamic states. So this was all for today. See you next time.